So in the first part, we talked about BMOS transistors and their structures, their analysis. And now we're going to talk about, mainly about the applications of either NMOS or BMOS transistors. So to know better idea about how can we use this, this device, we should put it in a circuit and, derive some equation or relation that relates V output to V input of the circuit. So that based on that shape, which is like transfer characteristics, as we agreed before, we're gonna, know what kind of applications we can use this transistor at. Okay, so in the beginning, we're gonna study the transfer characteristics of our MOSFET. Okay, so here we have a circuit in which we have RD, we have VDD, and we have a variable VGS. So VGS here is variable; it's not constant. Okay, and we're gonna change this. We will assume that this VGS is changing from minus infinity to infinity, and in each change, we're gonna see how much will be the output. Okay, this is basically the idea of transfer characteristics, either in BJT transistor or MOSFET transistor, whatever it is. Good. So this is what we're gonna do. We're gonna change VGS from minus infinity to infinity, and we're gonna check VO, which is VDS, for all these ranges. Okay, what we're gonna see is something like this. This is minus infinity, this is infinity. We'll assume this whole range into three pieces. So the first piece start, end is at that point, which we'll call VGS on, and the last portion or the third portion will start at what is called VGS set. So basically, between these two transition points, we will have these two transition points will divide, the operation of transistor into three regions. The first one is cutoff, in which VGS is less than VGS on. Then between VGS on and VGS set, we have another region of operation, which is the saturation region. So here VGS is larger than VGS on and less than VGS set. And for VGS larger than VGS set, we will work in linear. Okay, good. So why I call the first point VGS on? Because this is the point at which the transistor will turn on. I mean, before this point, when VGS is less than VGS on, we have current equal to 0. Okay, so for the first range in which VGS is less than V threshold, basically the transistor is off. And of course, VGS on is actually V threshold, because we know when VGS equal to V threshold, there will be a channel between the drain and the source, and a current can flow in that channel. So before V threshold, no channel, transistor is off, so the current is off. I is equal to 0, ID. So when we apply this here, we will find that VDS, which is VO, equal to VDD minus ID, RD. ID is 0, so this is basically VDD. So whenever the transistor is off, the output of that circuit will be VDD. Good. So the first point, let's make it, you know, that's fine. So the second point now, VGS set. This is the point, you know, at which the transistor will go from saturation to linear if VGS is increasing, or if VGS is decreasing, it will transition from linear to saturation. Okay, so this is the edge of saturation or linear. An edge is something in between. So at that point, VDS equal to VDS set, which is VGS minus V threshold. So let's determine it. So in the lab yesterday, we just write an equation, but we don't know from where this equation came. We will see now. So since we still at saturation, because we are at the edge of saturation, so we still belong to saturation, ID, and remember, since we changing VGS, you know, there is, you know, AC and DC part in general. So I mix, you know, small letters for the symbols and capital letters for the subscripts to say that, okay, we have AC and DC, or AC superimposed on some DC. So ID will equal to half Kn VGS minus V threshold square. Remember, we want now to calculate or find an equation for VGS to calculate this guy. Okay. We know also from the circuit that VDS is equal to VDD minus ID RD. And VDS in that point equal to VDS set, which is equal to VGS minus V threshold. And particularly at that, you know, at the edge now, we want to determine the VGS value that makes the transistor at that edge point. So this is VGS set, basically. Good. So VDD, which is VGS set minus V threshold, equal to VDD minus ID, which is half Kn VGS set minus V threshold square RD. So this equation is only has only one unknown, which is VGS set, the point of the input at which we will be on the edge of saturation. We consider all other values are known, like VDD, V threshold, Kn, RD. Okay? So based on that, we can simplify this into the following equation, in which we have minus half Kn RD VGS set square plus VGS set times Kn RD V threshold minus 1 plus V threshold plus VDD minus half Kn RD V threshold square. This is equal to 0. And of course, don't, you know, try to memorize this equation, you know. Usually when we we're gonna use it. We will have VDD will be known, RD will be known, okay, and Kn will be known. So we can just, integrate the numbers, and it will be easier, to read and satisfy. So we can take example. So, but basically, this equation, if we know VDD, if we know RD, if we know Kn, if we know V threshold, will give you two possible solutions. But you will find that one of them is less than V threshold, which is wrong. And the other solution, let's write it solution 1 and solution 2. And solution 2 will be larger than or equal to V threshold, which is accepted, of course. Or larger than V threshold, not even equal, larger than V threshold. Because we are away from the switching point from off to on. Okay? So this is how to determine VGS set. If we assume that the input is increasing until some point, we're gonna move from saturation to linear, and this point, the input at that point is called VGS set. Okay. But how about the relation between VGS or the input and the VDS in that region? Okay. So that will give us, the great idea about how we can use transistors. So I will go into conclusions directly. Okay. Also, we will make the derivation in another slide. But basically, what we will get, or the relation between VGS or V input and V output, which is VDS, is something like this. So we have two transition points. We have VGS on, which is V threshold, and we have VGS set, in which you can calculate from this equation, very big equation. So in the beginning, we will have VDD. Then we will have, as we will see later, it's a quadratic relation between VGS or V input and V output. So it will be something like this. It's a little bit curvy, especially at the end. Then the third, so this is, first and second region. Now the third region. It's also a quadratic relation, although most of the time VDS will be very small. So it's decreasing like this, but almost flat. Although it's decreasing, but very, with a very slow rate. Very slow rate. So it's just like flat, as we will see, as we saw also yesterday in the lab. Okay. So basically, if we name this 1 and 2, here is cutoff, here is linear, and number 3 here is the saturation region. So in regions 1 and 2, we can use the transistor as inverter. So it has two applications. Number 1, as inverter in digital circuits. And why? Because V input is low, and low means less than V threshold. The output of VDS will be high, VDD. And when the input, much larger than, or VGS set, we will have low output. So it's inverting. If you have input high, you will have output low. If you have input low, you will have output high. And in region 3, we can use a transistor as amplifier. As we will see in the next slide, we can even have a linear relation if at certain conditions for the input, and we will see that there is a gain, really. There is amplification. So let's see that.